Hello, this is Mr. P, and today we're going to talk about geometric sequences. The geometric sequence is formed by, once we know one of our terms, like a sub 1, we're going to multiply by a number to get our second term, a sub 2, and then we're going to multiply by the same number to get a sub 3, by that same number to get a sub 4, etc. We call this number the common ratio. Now this sequence differs from the arithmetic sequence that we already learned about, because instead of adding or subtracting a common difference, we're multiplying or dividing by a common ratio. And remember that division is just multiplying by the reciprocal, so we're really always multiplying by the common ratio. And a way to get the common ratio is we can take any two consecutive numbers in the sequence, for example, a sub 3 and a sub 2, and we simply do a sub 3 divided by a sub 2, and that is going to give us our value for r, which is the common ratio. Likewise, we can find a formula for the nth term of a geometric sequence, and it is very similar to the idea of the arithmetic nth term for an arithmetic sequence. If you remember from the previous lecture that for an arithmetic sequence, your nth term is going to be the first term plus n minus 1 differences. Well, here it's going to be the first term again, and then times n minus 1 ratios. So a sub n is a sub 1 times r to the n minus 1. So we can see that a sub 1 is our first term. Our second term would be a sub 1 times the common ratio. Our third term would be a sub 1 times two common ratios, etc., etc. And of course, we can define this recursively by saying that any term in the sequence, a sub n, is simply the previous term, a sub n minus 1, times the common ratio. Or rearranged a little differently, like we saw right here, we can say that any term in the sequence divided by the term before it will give you the common ratio. So either of those two can be used to define it recursively. Alright, so let's jump into some examples here. First of all, they want us to write the first 5 terms of a geometric sequence. They give us the first term is 3, and the common ratio is 2. Well then, our solution here is we're going to use the idea that we're going to start with the first term, which is 3, and then we're going to keep multiplying by 2. So a sub 1, of course, is going to be 3. That was the first term that was given to us. To get a sub 2, we simply multiply this times 2 to get 6, or using the nth term, it would be 3 times 2 to the 1. And then if we multiply by 2 again, we're going to get 12. If we multiply by 2 again, we're going to get 24. And multiply by 2 again, we're going to get 48. Or you can use the general term in order to jump straight to it by saying 3 times 2 to the n minus 1, n being 5, would be 3 times 2 to the 4th, which is 48. Alright, so that would be our first 5 terms. And then let's look at another example. Let's say they wanted us to find the 15th term of a geometric sequence, and they give us that the first term is 20, and the common ratio is 1.05. Well, right off the bat, we should know that we can use the nth term. We can use the formula for the nth term. That's a sub 1 times r to the n minus 1. And we just recognize that a sub 1, that was 20, that was given to us the first term. R, the common ratio, is 1.05. And n is 15 because we want the 15th term. So substituting in those numbers and a little bit of algebra, you should get approximately, or actually a little bit of arithmetic, you should get approximately 39.60. Alright, let's look at, sometimes they'll give you, not the general term, but they'll give you just the sequence. They'll show you how the sequence starts. And they're asking for us to find the formula for the nth term. We have to come up with the rule. And then they also want to know what is the 9th term. Well, once we have the rule, then we can find what any nth term is, so let's start with that. We know that a sub 1 is 5. That's our first term. And to find the ratio, we can simply divide any number by its previous term. So 15 divided by 5, that would give us 3, so the common ratio is 3. And then, like we said, we already know that a sub 1 is 5. So the general form, the general formula, must be a sub 1 times r to the n minus 1 is 5 times 3 to the n minus 1. Now with this formula, I can find any term, and they want the ninth term, which means n is 9. So substituting in n equals 9 gives me this expression. And simplify it, you get 32,805. All right, let's look at some more examples, of course. Here we have a two-parter. They want us to find the ninth term of this geometric sequence, and they do tell us it's geometric. And then also they want us to find a recursive formula for the sequence. All right, so the first part, we do know that the initial term is 10, so a sub 1 is 10. And we can find the value of r by simply taking any term and divide by the previous term. So 9 divided by 10, that would give us 9/10 as the common ratio. So our a sub 1 is 10, our r is 9/10, and now we can use that to find that the nth term would be a sub 1 times r to the n minus 1. And specifically, we want the ninth term, which makes n being 9. So that's 10 times 9/10 to the 9 minus 1. And when you clean that up a little bit with the calculator, you're going to get 4.3046721. All right, so that answers part A. What's the ninth term? Or we can answer part B for the recursive formula. We can think of this as if the first term is 10 and the common ratio is 9/10, then we can simply use the fact that a sub n is going to be 9/10 times the term before it, but you do also have to identify a starting point. You know, that it would not be, if they ask for a recursive formula, it's not enough just to give the recursive rule. You have to actually also say where it starts. Because you could have a different starting point and the same formula is going to give you a different sequence. So it is important to know that the first term is 10, therefore our a sub 1 is 10, and we simply use any term is simply 9/10 of the previous term. All right, let's look at, again, finding some specific terms in a sequence. So the fourth term of a geometric sequence is 125, and the 10th term is 125 over 64, and they want us to find the 14th term and assume that the terms of the sequence are positive. In other words, since 4 and 10 are even numbers, there is a possibility that it could have fluctuated positive, negative, if there was a -1 to some exponent. But this additional information they gave us tells us that that does not happen. All right, so for our solution, we're going to start with the 10th term in relation to the 4th term by the fact that the 10th term would be the 4th term times 6 ratios. If you went from the 4th term to the 5th term, you multiply by 1 ratio. To go from the 4th term to the 7th term, or to the 6th term, it would be 2 ratios, etc. So to go from 4 to 10, we're multiplying by 6 ratios. So this here means I can substitute in, I know what a sub 10 is, I know what a sub 4 is, substitute those in. I can solve for r and find that r is 1/2. Once I know that, then I can find the 14th term by simply taking a sub 14 would be a sub 10 times 4 more ratios. Or in other words, plugging in the numbers, I get 125 over 1024. I could also have done it by writing the general rule for the nth term and then plugging in 14 for n. Either way would have worked. All right, let's look at now, what if more than just the writing down the sequences. What if we wanted, sorry, excuse me, what if we wanted to actually sum these up? So we want to find the sum of a finite geometric sequence. And there is a nice little formula here. And if we go a sub 1 all the way through the nth term, a sub 1 times r to the n minus 1, then as long as the common ratio is not 1, then this sum, and we will see the derivation of this formula when we do induction later on, but this sum is going to be the first term times 1 minus r to the n over 1 minus r. And again, we'll see the derivation of this later. For right now, we're just going to use the formula. But starting with this formula, I do want to investigate what happens here as n gets larger and larger. So here we have, this is for a finite geometric sequence, but I want you to consider the following: that this expression here is going to approach, remember, since r is a value smaller than 1, r is a fraction, then we can find a sum of an infinite geometric sequence, because the only way there will be a sum is if the terms are getting smaller, which means your ratio must be between 0 and 1. But as you raise a fraction less than 1 but above 0 to a higher and higher power, that number is going to get smaller and smaller. So this expression approaches this expression, because r to the n approaches 0 as your n approaches infinity. So as n gets larger and larger and larger, a higher power of a small number is going to get smaller and smaller, small meaning less than 1, so it is going to approach 0. So therefore 1 minus 0 is just 1, which means that we can come up with this rule as 1. As long as that magnitude of the common ratio is less than 1, then we can sum up an infinite series going from 0 to infinity of just the first term, which is the a sub 1. A sub 1 times 1 would be a sub 1 over 1 minus r. So we have a formula for a finite geometric sequence, and we have a formula for an infinite geometric series. We can find the sum of both. And let's, of course, look at an example of this. Let's say we wanted to find the sum from 1 to 12 of this sequence. Now, of course, we can do it by hand. We can do it the long way. Substitute 1 for n, then substitute 2 for n, then 3 for n, etc., and add them all up. Or we can use the shortcut formula here. We can say that, well, our first term is going to be 1.2, because 4 times 0.3 is going to be 1.2. And then r to the n, r would be 0.3 is going to be the r, and n, because we wanted the first 12 here, so n would be 12. And substituting that, we get this expression, which of course simplifies to approximately 1.71. Now, there is a way to do this in the calculator, and I do want to actually show you that. So let me pull up my calculator here. The idea here, we learned how to find a sequence on the calculator. Now what we want to do is we want to take a sum of that sequence. And this is what the syntax is going to look like. I'll just put it up there for reference. But what I want to do here is, first of all, in my mode, I want to make sure I'm in sequential mode. And then on my home screen, I want to go second stat, which gives me the list. I want to go over to math and I'm going to choose number 5, which is the sum. So I want the sum of, now I want the sum of a sequence. So within the sum, I'm going to go again back to second stat, which is my list menu. This time over to operations, and again choose number 5, which is sequence. So I want the sum of the sequence. And now the syntax is the general term. So it's going to be 4 times 0.3 to the n. So the sequence is going to be the general term, comma, the indexing variable, comma, the lower limit, which is 1, comma, the upper limit, which is 12. And then an additional parameter is I can do comma 2 if I wanted to count by 2s or count by 3s, but I don't want that, so I'm just going to leave it the way it is. So I'm closing the parenthesis for the sequence, and now I'm closing the parenthesis for the sum. And when you hit enter, you should get the 1.714, etc. So you can see you get the same number on the calculator approximately as you do if you do it that way. So I do want to make sure you understand that to do a summation on the calculator, doing the summation notation, it's sum of the sequence. Alright, let's look at another example. Here we need to find the sum S sub n of the first n terms of this sequence. And this is the set of numbers where it's 1/2 to the n. So looking at a sequence can be 1/2, 1/4, 1/8, etc., all the way up to whatever n is. Now notice how they don't tell us what n is, so we need to come up with a formula for this sum. And the way we're going to reason through this is we're going to think of, we want the sum as, and we're going to use k as our indexing variable, as k goes from 1 to n, because I don't know what n is yet, of 1/2 to the k, which is that rule. So that's 1/2 plus 1/4 plus 1/8 all the way up to 1/2 to the n. So now we're going to use our formula for the sum of a finite geometric sequence, because we're going from 1 to n, so it's not infinite. And that is a sub 1, which we know is 1/2. 1 minus r to the n, r is 1/2. And that's all over 1 minus r. And cleaning that up a little bit, we can write this as 1 minus 1/2 is 1/2. The 1/2s are going to cancel, and you get 1 minus 1/2 to the n. So there's a formula that will help us find the sum of the first n terms, no matter what n is. So if I want to know in this sequence, in this geometric sequence, what is the sum of the first 100 terms? Well, it will be 1 minus 1/2 to the 100th power. Excuse me. Alright, let's look at another sum. This time they want us to find the sum of this geometric series. And it's an infinite one. The ... means it's going on forever. And here we don't know what the general term is. They haven't given that to us, but we can figure it out because we know that a sub 1 is 2, and we know that r, the ratio, will be any term divided by the previous term. So right away I know that the first term is 2, and the second term I can do 4/3 divided by 2 would be 2/3. So r is going to be 2/3. Now I know everything I need to know. Since the magnitude of r is less than 1, so 2/3 is less than 1, therefore we can say the sum of this series, this geometric series, is a sub 1, which is the first term, divided by 1 minus r. And 1 minus 2/3 is 1/3. 2 divided by 1/3 is the same as 2 times 3, which is 6. And finally, they might ask for something called the partial sum. And if they want here, they want us to use the graphing utility, we're going to find the first 6 partial sums. The partial sums are the sums of of the first 6 terms, would be the sixth partial sum. The sum of the 5 terms would be the fifth partial sum, etc. So the way we're going to do this is, and I'm going to show you the book solution. They're telling you you're going to use the cumulative sum feature in the calculator. You can do them individually and find out that these are the sums and continue adding them up, but the calculator is going to be a much easier way to do this. So let's look at, first of all, we're using the formula for the sum of an infinite geometric series. Oh, wait a minute, we're getting ahead of ourselves. Let me show you that first part. Let me show you how to get these on the calculator. So using the cumulative sum feature, we're going to go back to here. I'm going to clear that. And they want, where are my numbers here? Okay, here's our series. So we're going to go second list, and I'm looking for cumulative sum, which is right there, number 6. So I want the cumulative sum of the sequence. So now I'm going to go back into second stat, which is the list. And so it's the cumulative sum of the sequence. So now I choose 5. And we want 4 times 0.6 to the n minus 1. Now notice how when I'm raising it to an exponent that has more than one term, I do need to open a new parenthesis for that exponent. So it's n minus 1. Close the parenthesis. So it's the cumulative sum of the sequence of, now the syntax is the general term, comma, the indexing variable, which is n, comma, the lower bound, which is 1, then comma, the upper bound, which in this case they wanted the first 6 partial sums, so we're going up to 6. In other words, this is the sequence of this general term as n goes from 1 to 6. So I close the parenthesis for the sequence, close the parenthesis for the cumulative sum, and when I hit enter, I should get those numbers. 4, 6.4, 7.84, and if I want the other numbers, I again just keep scrolling to the right. There's the 8.704. There's the 9.22, 9.2224, etc. And you can see we can get all the numbers just by arrowing to the right. Alright, so again, the syntax will look just like this. It's the cumulative sum of the sequence of the nth term, the formula for the nth term, as n goes from 1 to 6. And that'll give you the numbers. Now, once we find those cumulative sums, which are also the partial sums, they also want us to find the sum of the series. And we can use the formula for that, because this is an infinite series, so it's going to be a sub 1 over 1 minus r. And when we simply look at the a sub 1 was 4, that was our first number. So it's 4 over 1 minus, the r was 0.6. So 1 minus 0.6 is 0.4, 4 divided by 0.4 is 10, and that will be our sum of this infinite geometric series. And we're done.